Good evening. Our topic will be classic oscillations, and our team is conformed by Alberto Ramos, Mario Alberto Cruz, and Angela Ramos. Next, please. Well, our topic will focus on the dampened oscillations with using the net or ordinary differential equations, because our problem is a mass attached to a spring and has friction depending on the type of environment that it is. In this case, we are going to use this differential equation we see. And the first term is Newton's second law. The second term is the damping constant times velocity. And finally, our third term is Hooke's law. In this case, we can see it as physically as is. If it is under damped, it will reach more rapidly to zero. If it's critical, it will oscillate above zero. And if it is over damped, it will oscillate not reaching zero. If we put it in a graph that is the ratio between the position we have to the initial position versus time. In this case, M represents our mass, B is the damping constant, and K is the elastic constant of the spring. And we can transform this equation to a more easy one to use. In this case, an equation that is similar to a polynomial of order 2. Next.
With this polynomial, we can find its roots by using the general formula. In here, we can see that the square root can have 3 different values. It could be negative, it could be positive, or it could be 0. With this, we can find which movement we are talking about. When our constant damping oscillation is less than our mass and our elastic constant, that means that it's an underdamped movement. When it's equal, that means that it's a critically damped movement. And when the constant of damping is bigger than our mass and our elastic constant, that means that we're talking about an over-damped movement. Now, we can find the solutions for each movement like this, meaning that the 3 movements will have 3 different values for the solution at different points, and that they will oscillate differently from each other. Here we have our number beta, which is equal to B, our damping constant, divided by 2 times our mass, and our omega 0. This omega 0 is our initial value for the condition that we are using our damped oscillations. For this, we decided to use the Runge-Kutta method of order 4, which uses the values of the graph for a much better approximation, using the increment of the slope in the beginning of the interval, the increment of the slope in the midpoint of the interval, then the increment of the midpoint of the interval, and then the increment of the slope at the end of the interval. With these ones, we can have a better graph-centered analysis of our approximation.
Analysis and numerical result. Now we see the coding for the program for the 3 types for classical oscillation: over damping, under, and critical damping oscillation. The first, we are going to integrate the function we need, in this case the 3 function, the oscillation, the damping oscillation. The next is for here, put the constant we need in the equation, the 2 equations for the damping oscillation and the Runge-Kutta method. And then for the function for the Runge-Kutta method, in this case for the last function. In the result is, in this case, is for the omega and r. The next, please. Now we have 3 examples. In this case, the first example is for the overdamping oscillation. This is the constant beta 1, the omega 4, and the other constants. And the first column for the result is for the iteration for the Runge-Kutta method, and the second column for the result is for the equation for the damping oscillation, in this case for the overdamping oscillation. And next, please. This example is for the 1/2 to time W0 in this graphic for the first line. The previous one, please. The second is for the other damping oscillation, in this case the beta is 7 and the omega is 2, the results, and the next, please. In the graphic is for the 8/8 of times the omega 0. Previous one, please. And the last example in this case is for the beta equal to omega equal to 4, and is for the critical damping oscillation. Next, please. Is for the 1/4 to time the omega 0 in this graphic, in this case the second line. Next, please.
Finally, our conclusions are that the numerical methods have many advantages in physics because it can make things more simple to solve if we have big data of it, or very difficult data to operate with. So we have to use them. It's easy because we can work with it with a differential equations like we did in this case, and it will give us results that are very precise, as compared to analytically. Also it will have very little error. And the Runge-Kutta method here will give us gave us a very easy way to work with these oscillations, because we just have to put certain initial values, and the program we have will give us all the results and will show the behavior of the kind of system we are working with. Next, please. Here are our references, and thanks for your attention.